Before we can really grasp the calculus involved in curve sketching, we must have a solid understanding of functions and their definitions. Of course, we can graph many different equations that don't all represent functions, but by investigating the rules that define what a function is, we will gain a much deeper understanding of why aspects of calculus work, such as limits of functions, tangents, gradients, and differentiation. Firstly, any curve that we sketch can be defined as a relation, since a relation is simply a relationship between two variables. For example, a relationship between two variables could be something like y is always the inverse of its corresponding x value. We can write this relationship as an algebraic rule, as we know that an inverse means a fraction, and this would give us that y is equal to 1 over x. The algebraic rule that defines their relationship is the equation that we're trying to sketch, so in our case, our sketch results in a hyperbola. But while every curve is a relation, not every curve is a function. A function is a special kind of relation whereby every single x value on the curve is unique, and therefore no x value occurs twice. For example, the set of ordered pairs 1, 1, 2, 2, 3, 3, and 4, 4 is a function as there are no repeated x values. However, if we added another coordinate, say 1 minus 1, this set is no longer classified as a function, as the x value x equals 1 now contains two corresponding y values, y equals 1 and y equals minus 1, so x is no longer unique. We can test if a relation is a function very quickly by either observing the coordinates to ensure that no x value is used twice, or by sketching the curve and drawing a vertical line through it. Since a function only uses any x value once, a vertical line will only cut it in one place. If it cuts it more than once, then the x value has been used more than once, and so it's not a function. If we are working with a function, then we can replace the y values on our axis with the notation f of x, meaning the function's value for each unique x value. It's often useful to think of a function like a machine that will output a unique y value for any x value that's put into it. Mathematically, this means that for every x value we substitute into the equation of a function, we obtain only one y value. Looking at the equation in the example, we know that 2x squared minus x plus 3 gives us a basic parabola. And by observing a quick sketch, we can see that this parabola will pass the vertical line test, and so therefore we are working with a function. The notation used here in our example is asking us to find the function's value when x is equal to -1 and the function's value when x is equal to x plus h. By inputting our given x values into our equation, we will obtain the unique y value that matches it in its coordinate. So, when x is equal to -1, the function's value is equal to 2 times -1 squared minus -1 plus 3, which upon evaluation gives us +6. And so we'll have the unique coordinate -1, 6 in our graph. Similarly, the function's value when x is equal to x plus h gives us 2 outside of x plus h squared minus x plus h plus 3. Since our x value in this particular example is algebraic, then our corresponding y value will also be algebraic. And so now we are just simply required to expand the expression given and simplify it as much as possible. So working from left to right, we would have 2x squared plus 4xh plus 2h squared minus x minus h plus 3. There are no like terms in this expression, and so therefore it cannot be simplified further.